The final session of the EFI project. I'll just say a few words about how the project's going to continue. So there's two more stages. The next stage is going to be online. There's going to be intensive discussion of all of the papers, and the participants are going to be active in that, and you should participate too. And then after that, there's going to be a workshop involving all 12 speakers, and it's going to issue forth in a volume, which will have commentary and discussion. So for our last talk, it's a great pleasure to have Menachem Magidor of the Hebrew University of Jerusalem. He's made fundamental contributions to practically every area of set theory. Two notable contributions are, first, his result that, assuming the consistency of large cardinals, it's consistent that GCH first fails at Aleph Omega. And then second, his groundbreaking work with Foreman and Shalah on Martin's maximum and its connections with the continuum hypothesis, something that's going to figure in the talk today. So it's great to have him here to speak to us about why some set theories are more equal.
Okay, thank you very much. It's great to be here, and thank you for the opportunity of thinking about what I've been doing for the last 40 years or so. I mean, you do spend some time thinking about it, but really, as a practicing mathematician, you try to prove theorems, and the meaning of that. From time to time, you lay back a little bit and think about what you do and why you do. But it's a great opportunity to do it in a semi-serious way. I'm not claiming it's necessarily serious. Okay, so let's. So the title is "Some Set Theories Are More Equal." A little bit of the table of content or the outline of the talk. So we'll talk a little bit about the reason we have this series of talk, which is independence problems. The title already of this section says something, the ugly monster of independence. This is not my term, it's Erdős' term. Erdős, whenever he would run into a problem he was working on, it will turn out to be independent, he would say, the ugly monster of independence raised its head again. So, by the way, this terminology has something to say about the attitude toward independent problems. The central theme, if Peter will allow me, of these talks has been to what extent we can afford to have pluralistic set theory, namely to have many different kinds of set theories. We'll talk about it a little bit. So the issue is pluralism in set theory. Is that something which is a tenable position? I'll try to argue that it's a problematic position, but this is my personal favorite. I'll try to build, does it matter? Does the decision about what is the favored or the right set theory, does it matter to the set theory, to mathematics, to science? We talk about the search for new axioms, trying to deal with the independence. We can even raise the possibility, maybe far-fetched, maybe a little bit of science fiction, can set theory be relevant to physics? We'll talk about some approaches of how do you try to reduce independence by trying to extend set theory in a particular direction, and some of the reasons for doing that. There were three directions we'll talk about: the ultimate L, forcing axioms, definable versions of the continuum problem, and we'll finish with some ending remarks. Okay. Now, when the continuum hypothesis was shown to be independent, it was rather, I'm a little bit too young to be really part of the subject when it happened, but not too far away from that. And at least talking to several people who've been around, it was rather shocking in a way. It was shocking not just because such a central problem of set theory turned out to be undecided by the axioms. It's a very central problem. It's the first on Hilbert's list of problems. It it's the fact also that the standard set theory, the Zermelo-Frankel set theory with choice, gives so little information about such central problem. As we all know, if you ask what is the size of the continuum, as far as set theory, the continuum could be Aleph 1, which is the continuum hypothesis. It could be Aleph 2. It could be Aleph 211,086. It could be omega plus 17. It could be omega 1. Could be even singular. There is so little information that you can actually derive from the axioms about the size of the continuum for such a central problem that was rather shocking. I talked to just one story. Yanis Moskovakis was still a graduate student when Independent Wisconsin, and he told me about a party, logic group party, that in '63, when everybody was speculating and saying, well, there are independent problems, but something is basic continuum is not going to be independent. That was about 2 or 3 weeks before Paul Cohen announced for the first time his result. Now, this is somewhat surprising because people knew about it, that there are independent. I mean, you know about the incompleteness theorem. You know that there are independent problems. But somehow the feeling was that real problems in which you are really interested should not be independent. I mean, the incompleteness theorem is something that is obscure. It's something which doesn't come up naturally in mathematical practice. And that shouldn't be. 2 quotes on the reactions. Mostovsky, such results, talking about independence results, show that axiomatic set theory is hopelessly incomplete. If there are a multitude of set theories, then none of them can claim the central place in mathematics. If set theory was claiming to be the framework in which mathematics is formalized, something that unites the different concepts of mathematics, whether you talk about real numbers or groups, or they all can be embedded in set theory. It doesn't mean, of course, that the mathematician, when he thinks about groups or numbers, he doesn't think about them as the way you code it in set theory. But the fact that there is a formal framework in which everything can be included, it's something which indicated at least the perception of the central role of set theory. Dieudonné, beyond classical analysis, there are infinity of different mathematics. Mathematics now is in the plural, and for the time being, no definitive reason compels us to choose one rather than another. By the way, I don't know what he means by when he talks about classical analysis, but any reasonable definition of classical analysis, you're going to run into independent problems as well. So, even there, you're not getting away from the ugly monster of independence. Another example, which was in some sense locally in the field of people doing it, was the Whitehead problem. And the problem, my favorite, you can phrase it as a purely algebraic problem, but my favorite formulation is in terms of topological group. You're talking about a topological group which is abelian. It's compact, and it's pathwise connected. Every 2 points in a group, you can be connected by a path. And the issue is, you got examples of such groups, which are, take a product of copies of the unit circle. Unit circle is such group. You take a product, it's still a product. So the Whitehead problem was, to what extent this is the only examples of such groups. 73, Sherlock proved the Whitehead problem is independent. And even assuming CH, even with CH, you can have the problem can be answered yes, the problem can be answered no. A little bit of the shock that was felt in the field about it, you can read, this is a quote from Wikipedia. I don't know who is the anonymous author of describing the Whitehead problem. And I want to draw your attention to a few expressions that are being used here. Whitehead first posed the problem in the 1950s. Stein answered the question of affirmative or countable groups. Progress for larger groups was slow, and the problem was considered to be an important one in algebra for some years. Note that it was considered to be, maybe there is indication that it's not important anymore. Shelach result was completely unexpected. While the existence of undecidable statement had been known since Gödel's incompleteness theorem of 1931, previous examples of undecidable statements, such as the continuum hypothesis, had all been in pure set theory. The Whitehead problem was the first purely algebraic problem to be proved undecidable. See what happens here sociologically, the language being used. Well, it's completely unexpected. This is not the kind of problems that are going to be independent. There are independent problems. We know about Gödel's incompleteness theorem, but this is something which can happen in pure set theory. It doesn't happen for real mathematics in a way. And this is not pure set theory. So here is, we did discover that it's independent. And actually there were attempts, if you talked at that time with people doing topological groups or building group theory, some of them would try to ostracize the problem. They would say, okay, that means the problem really is not a topological problem, it's not really an algebraic problem, it's really a set theoretical problem. It doesn't belong to us anymore, though they spend a lot of effort trying to solve it. I think that, I hope nobody is insulted, I think that's a little bit intellectually dishonest to say that that's not a problem once you discover that it's independent. Okay, so the central theme, as I said, for the series of talks, I hope that Peter would agree with me, that was pluralism in mathematics. And you can identify a little bit, somewhat schematically, three positions that were presented here. There is a pluralist position which say it is a fact of life there are a multitude of set theories, and they are all equally legitimate. You're all kinds. Well, we all accept maybe Zermelo-Frankel with choices and natural axiom for set theory, but from then on there are all these possibilities: continuum hypothesis, not continuum hypothesis, Whitehead problem, true, false. As I said, that's a choice independent of the choice of what you decide about the continuum hypothesis. You can decide about cardinal arithmetic. You can decide about problems in topology, the Moore metrizable space conjecture. You can make all kind of different decisions. You get different extensions of ZFC, and they're all equally legitimate. We should allow pluralist. There is even a more dramatic position, which is, I call it agnostic pluralist, which say there are a multitude of set theories, but it really doesn't matter. If you think about set theories, framework for mathematics, mathematics need only a fragment of ZFC. Most of the mathematics being, most mathematician, that's probably true empirically, needs only a fragment of ZFC. The independent problems are really irrelevant. It's a little bit this attitude about the Whitehead problem that I mentioned before. If you turn out to be independent, then it's not really interesting. It's not really a natural problem. And of course, there is the non-pluralist, that there is a way of finding the right set theory or the favored set theory, and there are meaningful answers to the independent problems. Maybe we don't know them yet, but in particular to the problem about continuum hypothesis. By the way, I put the right set theory. You might say the favored set theory. This is not the same thing. The issue is, you make the decision based on some belief in some truth about what's out there, or you make the decision about a matter of expediency, or what set theory you would feel more comfortable. It's not the same thing. I must confess, though I will not elaborate on it, that I myself consider myself to be a realist in the sense that there is the right set theory, but it will be in some sense beside the point for this talk. Of course, Gödel got very strong conviction that there is a right set theory. Here is the famous quote: Cantor's conjecture must be either true or false, and its undecidability from the axioms can only mean that these axioms do not contain complete description of this reality, and such a belief is by no means chimerical, since it is possible to find out ways in which the decision of the question might nevertheless be obtained. It's, by the way, fascinating that Gödel wrote in 1947, before Paul Cohen, the only evidence available at that point was the consistency of the continuum hypothesis, of course, due to Gödel, and the fact that he says it's, this paper is written with the conviction that it's going to be independent. It has to do, of course, with Gödel believing that probably the continuum hypothesis is false on philosophical ground, but it's still very interesting that this level of conviction in that it's going to be independent, but you can find the right answer. Now, extreme pluralism, which says that essentially everything goes. Maybe it's a little bit unfair to Joel Lemkin's to his talk here. I had the pleasure, of course, of watching it on the web, the video version. That I would call it extreme pluralism. You cannot coherently assume that there is one unique universe of set theory, but there is multiverses of different universes, each with its own property. And even to the extreme that actually there is almost nothing which is correct across except for maybe ZFC, across the different universes of sets that you have. Even the fact that universes are not, the fact that whether something is well-founded or not, even that is not absolute across the universe. Mainly, a universe of set theory is something that satisfies the axiom of ZFC. It thinks itself to be well-founded, but from the point of view of another universe, it will thought to be non-well-founded, and completely everything goes. Analogy that Joel is drawing is that set theory is like geometry. Initially, there was the belief of Euclidean geometry was the only possible geometry. Now we know that there are, after Lobachevsky, Bolyai, actually Gauss originally, and then Riemann, that there are this multitude of geometries, and they're all legitimate, and geometry really doesn't study any particular geometry. He may be interested in one particular case, but he knows that that's only one case out of many different cases of geometry. And the fact that there are independent statements in geometry, it's not very surprising. Or take, not just geometry, take group theory. The fact that there are many different groups, there are abelian, non-abelian, free groups, non-free groups, and the fact, look at the statement of the group is abelian, that multiplication is commutative. That's independent statement. I mean, some groups satisfy it, some groups do not. In that sense, some universe of set theory satisfy continuum hypothesis, some of them do not, and when you study set theory, you essentially study the multitude of universes in the same sense that you study a multitude of groups. Now, this multiverse universe has got an internal problem, which is that if you pick a multiverse concept which is too broad, namely that the different universes that you play without, everything essentially goes, then if you think about the, across suppose you take that your multiverse contains all universes which are models of set theory. Definitely there are statements which the mathematical community want to be true, to be true across the board, which definitely not true for any model. Take the statement set theory is consistent. We know there is a model of set theory due to Gödel's second incompleteness theorem in which a model of set theory in which set theory thinks that set theory is inconsistent. But everybody working, I guess most of the working mathematicians would agree that set theory is consistent. So here is a statement that we all believe in the truth, but it's not true across the objects which you work. Now, if you try to say, okay, there are statements which do not follow from ZFC, but should be true across this multiverse, then you have the problem of deciding what is this theory. What is true across the multiverse, which you will agree past ZFC. You face the same problem of independence. You face the same problem of which extension of ZFC you're going to take, which will be true for across the multiverse. There are much more subtle arguments. What I say, if you want to see the multiverse concept contain all universes satisfying certain theory, the problem of determining the underlying theory is similar to the problem of determining the right set theory to some extent. There are actually much more subtle arguments were restricted versions of multiverse, like the so-called generic multiverse, are problematic. Woodin presented here one of the views. Peter Koellner in papers were dealing actually with this, the problematics of the even a more restricted version of the multiverse. But in some sense, these arguments are what you might call internal arguments. By the way, I'm distinguishing, that's a remark Peter remarked to me, from when Gödel was talking about justification of axioms, he was talking about intrinsic justification and extrinsic justification for axiom. What he meant, intrinsic justification means that it's something that you get by conceptual, I know I'm oversimplifying, conceptual analysis of the concepts involved, and therefore you adopt the axiom that follow from an understanding of what the concept is. Extrinsic justification is something that you don't immediately come from the analysis of the concepts, but it's something that you study the consequences of the axiom, and then you see that this is something that makes sense, that it explains a lot, and therefore you adopt it. I'm using a little bit different terminology, and therefore I call it external and internal. Namely, external means, internal means something that has to do with the theory itself, with the set theory itself. Namely, that what are the consequences or how it behaves, or it has to do also with the conceptual analysis. But whereas external analysis would be the impact on things outside of set theory, whether it's mathematics or whether, if that's a possibility at all, impact on science. By the way, this is not to say that the reason for doing set theory is only its impact outside of set theory for mathematics or for science. Set theory is a fascinating and important subject by itself, but definitely we are going to talk mostly about external arguments. Okay, so generic multiverse, namely that you got essentially collection of universes that are connected to each other by that each one of them that you got by closing off under generic extensions, forcing, and I'm not want to repeat the argument that was given here by Woodin against that. But the argument that I want to use against the pluralistic view is that is try to remember what is the mathematical goal of set theory. Why do we do set theory? Well, we do set theory because it's fun. It's fun, there are fascinating techniques, it's beautiful, and so on. But really, let's remember the original motivation. The original motivation is to provide a unified framework for mathematics, or at least a major part of mathematics, in which different mathematical concepts can be considered to be part of the same formal system. So, this is something that unites mathematics. Now, if you allow a multitude of universes, a multitude, it's you have a problem because the set theory is supposed to provide the traffic rules. So, in some sense, having a multiverse, many universes, it's like having a traffic law, traffic rules which changes from one street. Changes from one street to another. And provided that set theoretic truths are relevant to mathematical practice, we'll deal with it in the next section of the talk, then imagine a situation in which everything goes. Now consider the poor mathematicians, the group theorists that somehow ran into problems that require some set theoretical answers to settle. And what type of set theory you assume is that could be definitely relevant. I can give you a Whitehead problem as an example, but there are other examples. But now you got really infinitely or a huge number of possible set theories. So that working group theorist would have to specify not just whether he talks about abelian groups or non-abelian groups, whether free groups or non-free groups, whether nilpotent, non-nilpotent. Besides the group theoretical assumption, he would have to list the set theoretical assumptions that he or she would like to use. Now, if there are only a small number of possibilities, we as set theorists, maybe if the continuum hypothesis or L or a Martin axiom, we have a few possibilities that's still workable. But just imagine, and actually you can definitely imagine such situations, or there are almost examples like that, where it really matters for the problem whether what is the exponentiation function on the aleph n's, and whether, now I'm becoming a little bit more technical, whether at aleph omega plus 1 there is a reflection, a non-reflecting stationary set, there is no non-reflecting stationary set, whether, and could be relevant whether at aleph omega plus 1 behavior, at aleph omega square plus 1 something else happens. So you may have so just imagine that part of you dealing with group theory, suddenly you have to carry all this burden of this huge list of set theoretical assumptions. So I think that definitely beats the role of the of set theory as a unifying thing for unifying framework for mathematics, and maybe we can't avoid it. But in that case, it's very bad situation. My feeling is, and I'll try to give some examples, that it's not the case, that we can make a more coherent view of finding the right or the favored set theory, which a small number of set theories, which could be serve as a framework for mathematics. Now, the geometry analogy that you got all these different set theories is analogous to the goal of finding the right geometry for physical space. Whereas you may have different geometries, Euclidean, hyperbolic, elliptic geometry, you can have the different Riemannian geometries. Actually, we know now you continue many possible, substantially different geometries for, let's say, the four-dimensional space, for instance. But the question of finding, so the geometer is studying all of them, or studying some of them, a class of them, but the problem of finding the right or the favored set theory is similar to the goal of finding the right geometry for the physical space. So there, it's a meaningful question. Not all geometries are as appropriate for describing the physical space. In the same sense, the feeling is that not every set theory is appropriate for being the framework for mathematics. There may be several candidates at the present, but additional study can eliminate some of them. So in some sense, the set theorist is closer to the geometer that works together with the physicist, trying to find the geometry of the physical space. Okay, so now let's go to the issue, does it matter? Is it potentially, what set theory you pick, would it matter for the mathematics people do or for science? So there is a character whom I'm going to call the agnostic pluralist, and was saying 99% of the mathematics done today can be done in subsystem of ZFC, actually a small subsystem. So the decision about independent problems like CH is simply irrelevant to mathematical practice. It really, our agnostic pluralist sympathizes with the view that really, if the problem turned out to be independent, that it's very likely not a natural problem, and maybe we've been wrong in stating the problem in the first place, and definitely we should forget about it. And anyway, interesting problem will not be of this kind. Now, non-pluralist, which, as you can guess, I'm sympathetic with, would say that may be true right now, that 99% of the mathematics done today can be done in subsystem, small subsystem of ZFC. But mathematicians working in a particular place simply are not aware that many times using a higher set theory may be relevant to the problem they are studying. The Whitehead problem was an example. People working in abelian groups theory did not imagine that principles like Martin axiom, which cites Whitehead problem in one direction, diamond, I'm technical deciding it in the other direction, could be relevant to the problem they are studying. They were not aware. And in some sense, I'm not belittling in any way the achievement of Shelah by showing it, but his greatest achievement in the beginning of the Whitehead problem was simply realizing that these principles, these set theoretical principles, are relevant to the algebraic problem. Later, there become a lot of technical developments that actually the whole notion of the whole theory of proper forcings and iterations were actually were generated because of the Whitehead problem was the trigger for that. But really, the realization that here are principles that the algebraists were never looking at, which are relevant to their problem. So this is, I believe, very likely that you'll that will happen for other problem. So the algebraists, as I said, of the Whitehead problem did not dream that principles like diamond or Martin axiom were relevant. And it takes time before you realize that certain principles are relevant, certain techniques, certain concepts. Application of group theory. Group theory was not considered to be something which could be relevant, let's say, to number theory. It took a long time from the formulation of the concept of groups until it became useful for other field of mathematics. Now, our agnostic pluralist continues on. He's insistent. The problems that real mathematicians are studying will never shown to be independent of set theory. If it's a natural problem, then it's not going to be independent. And you hear such claims. Though before the solution of, there's a typo here, Wild's solution of Fermat-Last theorem, there were speculations that maybe the conjecture, the Fermat-Last theorem, is independent. But everybody agrees, okay, the fact that there was a proof, it's not surprising. It's not independent. And our agnostic pluralists would say, well, the same is true for other open problems of number theory, Riemann hypothesis, Goldbach conjecture, twin prime problem, etc., problems of analysis. If it's really a natural problem that the mathematicians were working in a particular field were justified in formulating, then problem is not going to be independent. I find it very difficult to believe. Because if you look at this principle, there is no formal criteria that you distinguish these problems from the, for instance, independent statements which produced by the proof of Gödel incompleteness theorem. The proofs, they are pi 0, 1 statements. Some of the problems here are pi 0, 1, some of them pi 0, 2, but it doesn't seem to be a kind of criteria that would say that this is the type of statement that is likely to be decided on the basis of basis theory, whether it's Peano arithmetic or Zermelo-Frankel. This is not. What? How do you know the difference? Peter, in a conversation we had before the talk, suggested that problems that seems to be independent always involve something which has to do with a very fast growth of something, of some problem of number theory, which tend to be independent. There is a problem of something growing very, very fast. You look for a certain procedure if it goes very, very fast. But consider, for instance, the problem of the twin prime problem, whether there are infinitely many twin primes. The twin primes, we don't know whether there are infinitely many or just finitely many, but definitely there are indications that they are very sparse in the natural numbers. So if you look at a function that enumerates them, it's going to be very quickly, probably growing very quickly. And so it doesn't seem to be a criteria to distinguish between a problem that's going to be independent and a problem that is not going to be independent. Now the issue is, do you think that the real quote mathematician has some mysterious intuition that saves them for formulating or studying independent problems? That somehow they're formulating all these open problems and somehow they avoid phrasing the independent problem. Okay. Now, so I find it very, very difficult to believe that problems that look formally, they look very similar, like, after all, Gödel incompleteness statement could be simply the statement that a particular polynomial with integer coefficients and no integer solutions, that looks like a genuine number theoretic problem. So why the particular, if that polynomial is picked in a particular way of that function, that Fermat-Last theorem is the form, some simple number theoretic function has no no solution. So why is that different than the polynomial produced by the Gödel incompleteness theorem? That's very difficult to perceive. So my guess is that eventually number theorists, analysts will run into, even in the class of problems which are considered to be natural, which are meaningful, they're going to run into independent problems. Okay, now our agnostic pluralist, if we stay within the number theory, our agnostic pluralist may say that most of the open problems of number theory are pi 0, 2. Namely, they look like, is there a chance of using the blackboard? They look like, for every x there exists a y, phi xy, where this is only bounded quantifiers. This is what we call pi, the whole delta 0, 1, or no, only bounded quantifiers. Or recursive. Okay, so the problem, look at it. Now, suppose that you are decide, and the problems I listed, all of them are either pi 0, 1, like the Goldbach conjecture, or at most pi 0, 2. I mean, the twin prime problem is pi 0, 2. It says that for every number, there exists a twin prime, a pair of twin primes which are bigger than that number. So it's a pi 0, 2 statement. So if you use, and suppose that problem, you should use some set theory in order to decide it. Then you're not really using set theory. What you're using is that something called the one consistency of the set theory you talk. You really talk about a pi 0, 2 statement, which simply says that what is the one consistency of a theory? It's simply you look at all the sigma, all the pi 0, 1, pi 0, 1 consequence of a theory, and you say this is consistent with, let's say, Peano arithmetic. And really what you're using the statement of the one consistency of the theory, really using a number theoretic statement. But now the question is why do you accept this principle as a valid number theoretic principle? It is true that the pi 0, 2 statement follows from set theory, and it follows from the one consistency of the theory. But why is it natural to accept the one consistency as a natural statement? After all, this is itself a pi 0, 2 statement. Why do you accept that as a natural axiom more than the statement of the problem you are trying to solve? The only reason I can understand that you can accept it, you say, okay, the pi 0, 2 statement is the one consistency is accepted because it really follows from a certain concept, from a certain picture of set theory that should have models and therefore should be accepted as a natural assumption. And therefore it's much more natural assumption than simply assuming the solution to the original problem. So we should accept the one consistency of the theory because the set theory seems to be intuitive plausible, because we developed some experience working with it and it seems consistent, etc. And therefore we are ready to accept it. Assuming the one consistency in that case would be a natural assumption. Higher set theory can even be more relevant to analysis. Borel determinacy, when you look at it, look like an honest analytic problem and needs higher set theory to be proved. Actually, Borel determinacy, this issue was being studied by non-set theorists. Actually, game theorists, Gell and Stewart, Morton Davis, and so on. It wasn't a set theoretical problem. Later, it became interesting set theoretical problem. Another example of a problem that turned out to be independent, fascinating problem, and we'll say something about it later. Consider bounded linear operators in Hilbert space. Modulo and you look at this algebra, you look at the compact operators. It is an ideal on this algebra. And you could look at the quotient algebra. The quotient algebra is a very natural algebra. And the issue is every automorphism of that algebra is, you get it by inner automorphism. Inner automorphism means that you got one operator that you take x to, there is a fixed a such that that you take the adjoint of x by a fixed operator. Is every automorphism comes from this form. This problem, which is a natural analytic problem, turns to be, again, one example of independent problem. CH implies the answer is no, that due to Phillips and Weaver. The proper forcing axiom, well studied axiom, we'll talk about it. Hopefully, we'll have time to say something about it. The answer is yes. This is a result of PFA is a result of Farah, Elias Farah. Okay, so now the agnostic pluralist tries again and says, suppose the problem of real mathematics is solved using some fancy set theoretical assumptions, like large cardinals or some other axioms. It will not be accepted by the mathematical community as a legitimate solution. After all, you're trying to solve the problem using standard methods. This is not standard methods. Now, I believe that if the problem will be solved by making set theoretical assumptions that looks intuitively appealing, fitting the mental image of the universe of sets, and non-arbitrary, it's not something you invented specifically to settle the problem, it doesn't seem to be ad hoc, then it will be accepted. Let me give an example, which I think is quite illustrative. When you look at Weil's proof of Fermat's theorem, it uses a notion called Grothendieck universes, which essentially means inaccessible cardinals. Now, everybody expected that could be eliminated. Fermat's theorem can be proved in Peano arithmetic, or even a subsystem of that. Actually, Agnes McIntyre suggested the plan of how to do it, how to eliminate the use of Grothendieck. Interesting thing is that so far, nobody bited the bullet. Nobody actually was trying to follow the McIntyre program. And when I talked to several number theorists, they simply did not care. They say, if you are assuming inaccessible, that's fine with us. That's perfectly good for us, a perfectly good solution proof of Fermat's theorem. This is a natural assumption. It looks very reasonable as far as our picture of the universe of set theory. We can assume without any problem, that there are Grothendieck universes, therefore a proper class of inaccessible cardinals, so that the fact that they are being used in the proof doesn't affect the trust in the truth of the result. This is a sociological fact, but I think it's illustrated. Now, suppose that the set theoretical methods can be eliminated. In fact, they maybe came naturally in the proof that real mathematician. By the way, my recent thing, I talked to it last week. I've been in Oxford, and I was talking to Andrew Wiles, and he doesn't care. For him, the proof stands with the use of inaccessible. That's a perfectly good proof. Okay, so even if it can be eliminated, then you can consider the set theoretical universe as a scaffold for the construction. And it may be that it will be very difficult to find a proof without that scaffold. So I believe that the set theory used is relevant to mathematical practice, and since the mathematician will run very likely into, almost in any field of mathematics, to independent problems, then what set theory you embed your structures you study is relevant and could make a difference. And I believe that mathematician will accept a solution based on the use of the right axioms. And the goal of set theorists is to come up with a coherent picture of the universe of set theory that will be acceptable as the framework in which important independent statements will be decided. So we start from our goal, the search for, it does matter which axioms, by which axioms we extend ZFC. So we go out and try to search for the right or the favored axioms for extending ZFC. And now again, the very famous quote of Gödel that says that even disregarding the intrinsic necessity of some new axiom, a probable decision about its proof is possible also by studying its success. Success here means fruitful in consequence. There might exist axioms so abundant in their verifiable consequences, shedding so much light upon a whole field and yielding such powerful methods for solving problems that no matter whether or not they are intrinsically necessary, they would have, when it talks about intrinsically necessary, it means that the conceptual analysis of the basic notions forces you to accept the axiom, they would have to be accepted at least in the same sense as any well-established physical theory. The analogy to physical theory is something, it's a theme that I would like to, physical theory or scientific theory, would like to explore. Now, when you talk about axiom, I want to make a remark that important colleague of ours, Pfefferman, here in talks here, was quoting the Oxford English Dictionary definition of an axiom, that an axiom is something which is self-evident proposition, requiring no formal demonstration to prove its truth, but received and assented as soon as mentioned. And he said definitely some of the things you now try to extend ZFC do not conform to this agreement. It's not something that you accept immediately. I, with all due modesty, beg to differ in the sense that this is too strong. An axiom can be adapted if there are process evaluations, comparing with alternatives, studying its consequences, etc. You can accept something as an axiom, as a genuine axiom, something which is very fundamental, not immediately, but after a process of study, of maybe comparing with competing axiom with other axiom candidates. And it will be a genuine axiom. Take, for instance, suppose you try to axiomatize quantum mechanics, physics. One of the axioms, I don't know exactly which formulas you will pick, but probably would say that your physical system is really the set of one-dimensional subspace of a Hilbert space. Is that something which is self-evident? Not at all. It took a long time of clarifications, of crystallizing that notion that this is really what a physical system should be. So this is an axiom which was adopted after a process of evaluation. But I still believe that new axiom, one of the criteria when you search for new axioms, should have some intuitive philosophical appeal. It should conform to some mental image of the basic concepts of set theory. Now, this is a vague principles. Most of the principles that I'm going to describe here are going to be vague, but and some of them may compete with each other. But it's something you should look for and say, okay, this is one of the criteria which I evaluate one axiom versus another options. In some sense, I would say that you should need, for a new axiom to be adopted, you need a good slogan. I'm a great believer in slogans, by the way. Slogans can be sometimes misleading, but sometimes they are very good slogans, vague, not very accurate slogans. I think even in science could be actually good guidance sometimes to formation of theory. So I think that when you study new axiom, you should have some kind of intuitive philosophical appeal. You should have a good slogan. Now, I would say more external criteria for evaluating axioms. Well, we try to fight independence. Therefore, the axiom candidate we consider should be strong enough to decide a large class of statements which are undecidable on the basis of axiom adopted so far. We have to get some benefit from adopting this axiom, so we have to make a decision. And the decision should be in something which is coherent, elegant theory for some important class of problems. One of the ways we test, and again, it's a vague criteria, but seems still a meaningful criteria, we should test the different axioms by the coherent, elegant theory which they form. The extent possible, the axiom should be a testable, verifiable consequence. Now, what is a verifiable consequence? Again, I'm vague on purpose. It could be that mathematical consequences are something we like. It's something that we expected. It's something that really fits, again, some mental image. I think that the fine example is for instance, the large cardinals that imply, for instance, projective determinacy. This is something that was, in some sense, expected. It filled the mental image that simple sets, simply definable sets should be well behaved. And here is something that the consequences are verifiable in the sense that they fit the mental image, but could be verifiable in a stronger sense. There could be something like, suppose it proves a pi01 statement, that there is no natural number which satisfies something. So the fact that you keep testing it, and so far you didn't run into counterexample, that's a verification. A verification in the same sense that physical theory is being tested. So you can be, suppose you believe in the consistency of set theory, then the fact that a physical fact that in the next 25 years you will not find a contradiction, that's a physical fact which so far it's being verified. Maybe we'll, at some point it will be falsified, but that's okay, we'll have to change our mind. Now, if possible, the axiom or a significant part of its major consequence should be resilient under forcing extensions. So we know that one way, while I'm make some concession to the multiverse, or the generic multiverse, in the sense that this is a way of changing our universe of set theories by forcing. And if some evidence for the axiom, if this is something that keeps, if you use the standard technique of changing universe of set theory, that doesn't, once you have the truth of the axiom, you can't change it anymore. This is, I think, an evidence for desirability of that of the axiom. Most of the large cardinal axioms, if you consider the proper class of these large cardinals, satisfy this thing. Now, verified consequence could mean the new axiom is a mathematical consequence that cannot be derived without them. It's unlikely to be falsifiable. I'll skip, I think that. Now, could we imagine a non-mathematical verification? Is it conceivable different set theories will be judged by their impact on fields outside of mathematics? Now, that looks very far-fetched, but I believe that it is possible that the set theory you use could have an impact on the scientific theory. It could be simplified, streamlined. You pick one set theory over another. And let me give you an example which is not exactly of this kind, but is not 100% convincing, but it definitely indicates possibilities. And I'm talking, making a disclaimer, we do not have a real example of physical theories are sensitive to the set theoretical context. But two related examples that it's not a sheer impossibility. Consider the Einstein-Podolsky-Rosen paradox and Bell's and CH-SH inequalities in physics, Cauchy-Specker theorem. You know, for lack of time, I'll go to the Cauchy-Specker and I'll explain to you you know, how set theory could be relevant to that thing. Just for curiosity, I think it's rather rare to find, this is a paper from, by Itamar Pitovsky from 1982. Unfortunately, Itamar is not with us anymore, died prematurely. But this is a rare case in which you got Physical Review Letter is a hardcore physical journal. And here is in the paper, there should be mention of Martin axiom here somewhere. I think that the first column, somewhere toward the middle, you find a mention of Martin axiom, so I think it's rather a curiosity. But what Pitovsky is doing, it changes a little bit the notion of probability, not too dramatically, but in a way which handles things which are otherwise impossible. Let me tell you something about the Cauchy-Specker theorem. I'm skipping something about the. Suppose you got a particle whose spin is 1. Namely, whenever you measure the spin along a certain axis, the possible values you get are 1, 0, or -1. Now, you know that if you take 3 mutually orthogonal axes, and you measure, you cannot measure simultaneously the spin along x, y, and z. But the absolute value can be measured simultaneously. It's the corresponding operators now in technical commute. And we know that they satisfy the sum of the absolute values is 2, namely exactly 2 of the spins. When you measure simultaneously the length of the spins along this axis, 2 of them are going to be 1, and 1 of them is going to be 0. What the hidden variable assumption claims that particles carry some predetermined value of what to be the result when you measure the spin along this axis. And the Cauchy-Specker theorem claims that this is impossible. It tells that there is no function defined on the unit sphere of the 3-dimensional unit sphere in the 3-dimensional space, so that for every x, Sx is either 1 or 0. Remember, it's the absolute value of the spin along this, such that for every triple of mutually orthogonal vectors, the sum would be 2. Simply, you can't do it. And really, it's a finitary theorem. It's no restriction of what the function, such a function does not exist. But now let's make a small change. And suppose we require that the function will satisfy that inequality almost everywhere. In what sense almost everywhere? In the sense that if you take, I'm very bad at drawing, but if you take a fixed vector x, and you look at a vector y for which the, once you determine y, then essentially you determine also z, the thing perpendicular to both of them. Then the set of possible y's is they form a great circle on the sphere. Then the set of y's is of measure 0 for a fixed x. The set of y of measure 0, which violate that equality, is of measure 0. And Pitofsky proved that assuming Martin axiom is able to find something which satisfies, which violates the Cauchy-Specker theorem almost everywhere in that sense. Call such a function a PKS function. And he used Martin axiom for that. So he got a kind of hidden variable version of the spin function, but he used Martin axiom for that. Relatively recent result of Farah and myself is that the fact that such a function exists, the fact that he used Martin axiom is necessary. You can't do it without some set theoretical assumption. Doesn't matter technicality of how you get models of set theory in which you cannot find a function like that. But here is something, something which can be, I won't say relevant to physics, it's more to the, this one, particular one, to the interpretation of physics, to the philosophy of physics, but set theoretical assumption start smelling that their consequence tell you something about whether a physical theory lives more comfortably in a certain set theoretical universe than another. I'm going to well, being well short, it's not impossible that scientific theorists will prefer one set theory over another because it makes the scientific theory simpler and more elegant. It may even be possible that in order to derive certain experimental testable results, one has to prefer one set theory over others. Again, it's not exactly that you will have experimental tests between different set theories, but explaining, let's say, theoretical experimental results, you may be more easy. It will be easier to do it in one context than another. Okay, now this criteria for choosing, looking for the right axiom, I suggested them as the principles of. They are not just the principle of expediency. It's not just a matter that it is convenient to get such, the more elegant set theory. I believe that they are really rational procedure for finding. Here, my realist self comes up. That it's a rational procedure of finding the right set theory in the same sense that the practice of science is a rational procedure for finding truth about the real world. Okay, let me go for the final segment of the talk. Let me go to the talking about some direction in which we can extend ZFC and get meaningful decision about a large class of independent problems. Just one preliminary remark. Large cardinals, assuming of large cardinals of different kinds, is such a success story that they've got wonderful consequences. They definitely fit a certain mental image. They can be justified by the right slogan. That I think that it's widely accepted by set theorists, and I think that the set theory we'll consider will be only those that allow essentially any kind of reasonable large cardinal. I will not go into the motivation of large cardinal. I'm skipping that. Okay, and we'll talk about three directions. We talk about something which was presented here by Woodin, which is called the ultimate L, forcing axioms, and definable versions of the continuum problem. Now, the ultimate L, you talk about L-like universes. Now, the motivation is that the universe of sets is constructed by a series of stages, indexed by the ordinal, so that every successor stage is rather a canonical extension of the previous stage. You do it The sets are grow step by step. It depends what type of procedure you apply, but there can be different ways of doing it. A study that I'm now doing with Juliette Kennedy and Jacob Van Allen is different ways of making these stages. But anyway, this is the mental picture that you have from something that looks like L. The constructible, Gödel's constructible universe is the first example. Advantage of L, it decides almost all current independent problems. Any interesting independent problem almost. There are few which I don't know the answers in L, but any kind of interesting problem, including CH, of course, GCH, are decided by L. Disadvantages of L, it's incompatible with large cardinals. And in most cases, it decides the independent problems in a less elegant direction, less coherent direction. L is a kind of, the constructible universe is a kind of paradise of counterexamples. You try to state a theorem that you have some feeling that should be true. L would give you a counterexample. That can be even formalized in a way. Now, the ultimate L is supposed to avoid the first disadvantage. It's still to be seen to what extent it avoids the second disadvantage. For instance, does it satisfy diamond? But again, the ultimate L was something that Woodin was pushing for something that would include any of the interesting large cardinals that we have. And the axiom V equal to the ultimate L could be a very appealing axiom candidate, provided, of course, that the ongoing work for doing it will be successful. Now, I want to spend just a few minutes making conjecture. I'm risking something here. Making conjecture that if the conjecture is true, then it will not. Then the ultimate L at least will not be done along the lines in which at least I knew about, was trying to do before. I understand there are versions which may avoid this conflicting with this conjecture. One of the remarkable theorem of Woodin tells you that you look at the sigma 2 1 sentences. Namely, it's a statement that talks about there exists a set of reals such that it satisfies something, and then all the quantifiers are over reals. Then, suppose you can force it. Then, if CH is true in the ground model, then it's really true. It's some kind of absoluteness. Now, sigma, when you try to extend it to larger class of sentences, then it's not true. And the conjecture is that the same thing is old if you assume the Ventura principle by Jensen, the diamond. If the conjecture is true, then at least the ultimate L, in the ultimate L will satisfy diamond, then either ultimate L cannot be constructed, and or one would have to find a different way of building it. I understand there are possibly different ways of doing it. But let me now move to another line of thought, which might extend ZFC and settle many of the problems, which is forcing axioms. And the slogan is that if you can imagine, if it is possible that a set having a given property is possible, and there is no clear obstruction to the existence of such a set, then such a set really exists. It's something, a richness axiom. It's something that the universe of set theory is rich enough that if you can imagine something to exist, then it really it exists. Now, as stated, it's not very consistent. And it's a very vague thing. But let's translate possible approximation to can be forced. This is our standard techniques for getting new sets into the universe of set theory. So the slogan changed. If one can force the existence of a set satisfying given property, there is no clear obstruction that is existent, then such a set exists. Now a more technical definition. You can't have it for every forcing. For instance, suppose you look at Aleph 1. You can force a function that maps Aleph 0 onto Aleph 1. You can make it countable. You can change the fact. This is so-called the Levy collapse. So you can imagine a set that witnesses that your present Aleph 1 is really countable. Such a set cannot exist in the present universe. So the principle as stated cannot be consistent. But the forcing axiom tells you that if your forcing is mild enough, then you can then you can do it. Again, because of lack of time, we'll not get through the formal definition. And now, again, I'll skip that. Now, the famous forcing axiom, there is all list of forcing axioms. So the first one is so-called Martin axiom, which tells you that it's the forcing axiom with the forcing notion you talk about, the mild, definition of mild if the forcing satisfies the countable chain condition, which is a mild thing, doesn't collapse cardinals, you know, a lot of what it does to the universe. Proper forcing axiom, the same thing applying to a larger class of forcing, which is proper. Again, the definition is technical due to Scheller. And Martin maximum is something which forcing axiom for class of forcing which do not destroy stationary subset of omega 1. And this is a maximal. It's called Martin maximum because it's a maximal version of that. You can't have this type of axiom for something which is destroyed stationary subset of omega 1. Now, Martin axiom, while deciding many independent problems, does not decide the size of the continuum. The continuum could be, it implies the continuum is bigger than an aleph 1, but it could be aleph 2, aleph 3. In some sense, almost the same level of independence you have about originally is not decided by Martin axiom. Now, a series of results in the original paper, which we introduced Forman and Scheller, for shows that this Martin maximum does give a particular value to the continuum. It tells you the continuum is exactly aleph 2. A sequence of results by Todorcevich, Velichkovich, Moore, and others show that any attempt to start, Martin axiom does not decide the size of the continuum, but any attempt to extend it along these lines by a little bit ends up in the same value for the continuum being aleph 2. Which is a remarkable fact. So I think that they are very appealing. And Martin maximum is something that gets you a lot of consequences. A lot of independent problems are decided by it. It has got some intuitive appeal. It's got the right slogan. Everything seems fine. So I would even recommend adopting it as an axiom and deciding the size of the continuum. It had an axiom candidate that was a competitor, which is Woodin axiom star, which is really an axiom about the structure of H omega 2. H omega 2 is the set which are hereditarily of size omega 1. And it gets many of the results of for H omega 2, including the fact the continuum is aleph 2, but it's not exactly the same. It got the character of being, again, a richness axiom. The word is rich, namely that if you can force that a pi 2 statement can be true in H omega 2, then it's really true for H omega 2 of the ground model. In order that would be equivalent to the original formulation of Woodin's star axiom, then you need a class of Woodin cardinals, but let's leave these technicalities. So both of them are appealing axioms. Are they compatible? Paul Larsen proved that assuming consistency for large cardinals, does not imply star, does not imply this axiom. The other direction is that star does not imply that's even easier in a way. Star is a more local axiom. But there is a natural strengthening of which is called which in some sense tells you, which, again, I don't want to get into technicalities. I wrote down here the technical definition, but I'll skip it. But in some sense, it tells you something about, you see, the forcing axiom tells you if you can imagine a set satisfying a certain property, then if you can force by a mild forcing, then this set exists. tell you something about the set that you, the witness that you get in the ground model before you force is even closer to the example you get in the extension. You are true about some stationary sets, will not get into the technicalities. Now, a natural conjecture is that Woodin not agree with that conjecture, but that implies the axiom star. So it is a way of, you got these two axioms which are not comparable, both of them very appealing, but that is the natural axiom that unifies both of them. Well, the conjecture is probably, if it's true, it serves as evidence for adopting both and star. The conjecture is probably true. I wasn't able to check. This conjecture was very likely proved recently, I mean, like last week. I mean, namely, it was claimed about 2 months ago, and then if somebody have a chance to look at the original version of the paper was put on the web here, I still use it not as a conjecture, but as a theorem, and then they found a gap in the proof. Last week, they apparently, I didn't have time to check all the details, they patched the gap. So the conjecture is not a conjecture anymore, and very likely. And so MM++ could be a very appealing axiom candidate, and implying that the continuum is exactly Aleph 2. Now my last line of thought about what it can decide many questions. And that's, again, you start with a slogan, some intuitive feeling. And that the size of the continuum should be determined by nice evidence. There should be nice evidence for why the continuum has got a certain size. So Tony Martin has got a paper about evidence. Koellner in the papers that are beautifully written, Peter, if I may say so, the one that preparing the ground for this series of talks, that actually identified that there are 3 versions of the continuum problem that what you might want is nice evidence for the continuum. So one of them would be that if you say that the continuum is bigger or equal than kappa, then you should have a nice set of reals having cardinality kappa. A well-ordering version would say that that you have a nice well-ordering of a set of reals whose order type is the size of the continuum. That's evidence the continuum has got a certain size. And there is the surjection version, that you should have a nice surjection of the reals onto the ordinal, which is the size of the continuum. Think about that as a ordinal, and you should have a nice surjection. That would be nice. And these 3 versions are not the same thing. If you don't consider especially nice, if you don't any sets, then under axiom of choice, of course, they are equivalent. But without it, if you talk about something which is definable, which is nice, then they are definitely not the same. And now the notion that I would like to use for nice is a notion of universally bare. So a set of reals is called universally bare if whenever you take a continuous function from the reals onto any topological space, from a topological space to the reals, and the set A, is a subset of the reals, is nice if the pre-image of A has got the bare property. It's namely, it's open set up to a set of first category. This is a very natural notion of a set of reals being nice, in the sense that it follows from that the fact that it's the bag measurable property of bare, many nice regularity property if the set is universally bare. So the nice continuum problem could become, for which cardinal kappa can we have a universally bare set of reals having cardinality kappa? For which cardinals kappa we can have a universally bare well-ordering of a set of reals in order type kappa? Universally bare well-ordering means that the well-ordering is a set of pairs is universally bare. For which cardinals we have a universally bare surjection of the reals on kappa? A surjection of the reals on kappa would be called universally bare if you look at the relation. In order to know the surjection of the reals you simply have to know for which pairs x and y fx is less or equal than fy. That determines the surjection completely. So the issue is if that set as a set of pairs is universally bare, that would be nice. Now there are open problems even in the general ZFC without any assumption about these problems. But if you assume a proper class of Woodin cardinals, then we know exactly what happens with the first 2 versions. Every universally bare set of reals is either countable or contains a perfect subset. It's either countable or a size of the continuum. It doesn't tell you anything about any intermediate value. Every universally bare well-ordering of set of reals is countable. It doesn't tell you anything. There is no well-ordering of which is nice. And by the way, that means some intuition, namely that, well, you can, by the axiom of choice, well-order the reals, but that well-ordering should not be too nice. in that case, the two first versions are not. Now the universally bare surjection problem was to try and attempt which ordinals you can have a universally bare surjection of the reals. And something that Peter was kind enough to call the Menachem Magidor program was to attempt to prove that ordinals on which you can have a surjection like that is of cardinality less or equal than aleph 1. There is a surjection of the universally bare, that's ZFC theorem, surjection of universally bare surjection of the reals on aleph 1, but the issue is to have it, that's a theorem that at least will follow from large cardinal. The conjecture was, or the program was killed by Woodin, namely by some set theoretical assumption, which, by the way, which follows from M, our axiom here. We know that there exists a surjection of the reals, a nice surjection of the reals onto omega 2. Namely, MM implies not just that the continuum is aleph 2, but you have a very nice evidence for the fact that it's aleph 2. You got a nice surjection of the reals on the ordinal aleph 2. Both MM and star implies the universally bare surjection of the reals onto aleph 2. So they not only determine the size of the continuum, but also determine there is a nice evidence for it. So the next conjecture may be true in ZFC, but getting from large cardinal will be extremely interesting. There is no known model in which there is a surjection of the reals, a nice surjection of the reals onto aleph 3. You can do it for aleph 2. We don't know that you can do for aleph 3. So a conjecture, I'm trying to revive to keep the so-called Magidor Foreman program alive, that if alpha is an ordinal such a universally bare surjection of the reals on it, then alpha is of cardinality at most aleph 2. That nice evidence for the size of the continuum, there is something inherent that it will never be more than of size aleph 2, if that conjecture is true. And then some scenarios how to prove it. I will not get into it. If I would know how to prove it, definitely, of course, I would shout it, but I don't. It's still... Okay, so let's summarize. We hold the truth to be self-evident, at least hopefully that we have some good arguments for them, that not all set theories are created equal. Some set theories, there are all kinds of criteria, whether the application of mathematics, whether they fit the mental image of set theory, they're not created equal. Some of them are better than others. The difference between set theoretical frameworks is relevant to mathematics and possibly to science. The choice of the right set theory is an ongoing process. In some way, similar, not identical to the process in which branch of science make a choice of preferred theory. You got candidates, you study the consequences, you test them, maybe not experimentally in that case, but you, against some mental images, against some the desirability of the results, and there are many different criteria for desirability of the results, and then you go, you prefer one direction rather than another. At any given time, there may be several competing theories. The decision between them will be based on their coherence with the mental images intuition about the basic concept of field, as well as consequence of the theory and its application in mathematics and science. The mental image and intuition may be refined over time with a better understanding of the consequence of any particular theoretical choice. Also, the criteria which we evaluate the axiom candidate may conflict with each other. But in that case, we may face, like we face in scientific theory, sometimes you got evidence for, evidence against, and we have somehow to weigh the different evidence and make the choice. What about continuum hypothesis, which is the problem that motivated this whole story? We suggested several directions to go. Interestingly enough, these directions suggested only two possible values for the continuum. One of them was that in ultimate L, the continuum hypothesis was true. The others, both the forcing axiom and the effective or the nice evidence for the size of a continuum, get the result of aleph 2. Again, they are based, all the three directions based on some conjectures, but I'll give you as an example. And it's a fascinating fact that this cardinal aleph 2 keeps popping up. And by the way, there are other cases in which somehow aleph 2 comes as a natural cardinal. It's an interesting historical fact that Gödel, toward the end of his life, thought that he has some natural reasons for believing that the continuum should be should be Aleph 2. The argument has got flaws. You can read the whole story in the Gether collected works. Actually, Solovey wrote the introduction to that. But it's still interesting that, again, he concentrated on Aleph 2 as a possible, as the natural value of the continuum. Well, the end result is that some set theories are more equal. They're not the same. Some of them are better than others for many different reasons. So let the best theory win. Thank you. No, it doesn't imply that the continuum is, it doesn't, no, it's not a matter of application, it's a matter of the natural thing. It will give you, maybe I misstated the case, it will give you, if you believe in the slogan that there should be a nice, definable evidence for the size of the continuum, then that conjecture will give you evidence for the continuum being at most Aleph 2. I'm sorry.
Yeah. I was just thinking that since there's an intuition going in the other direction, namely that the intuition is that we shouldn't have really good definable well orderings. So
it's not a well ordering.
No,
it's a pre-well ordering.
Yeah,
it's a suggestion. Yeah. No, I mean we know very well. You know it very well that you can have very nice surjection. For instance, in under AD, I mean. Axiom determinacy is definitely very far from being choice. So you don't have any well-ordering of the reals, any reasonable well-ordering of a set of reals, except for a countable set of reals. There is no uncountable well-ordering of any set of reals. But on the other end, there are surjection of the reals on actually on many in that model on Aleph 2, Aleph 3, up to theta, which is a relatively large cardinal. The point is, from the point of view of a model of choice, how large is that? That theta.
So you think even in the choice setting that the intuition is such that there should be a universally bare witness for the size and continuum?
Yeah. And you can have it under MM or star or something like that. You have this delta 1,3 surjection, which is definitely universally bare in that situation. And onto Aleph 2. But there is something, it seems like, again, there is something special about Aleph 2 which somehow blocks the, the thing that, the obstacle that you run in, I'm saying something which is trivial, but that triviality is actually, comes up in several arguments, several technical arguments. Namely, Aleph 2, if you look at ordinals less than Aleph 2, then you got only two possible cofinalities below it. Aleph 0 and Aleph 1. Now, Aleph 0 is a very special, every cofinality, countable cofinality, is a special case. I mean, the notion of a closed and bounded set in it, is not meaningful and so on. So having only one cofinality in which is only one uncountable cofinality, it's something that makes Aleph 2 rather special in all kinds of constructions, and that's there are all kinds of forcing construction which you can push, you can iterate up to Aleph 2 and try to get past Aleph 2. Aleph 2 is going to be collapsed. And if you analyze exactly what's going on, it's exactly that you have only one uncountable cofinality. Having two uncountable cofinalities, you run into a problem because they in some sense, if you think about iteration theorems and so on, they conflict with each other somehow. If you try to deal with the, again, I'm becoming technical, but if you try to deal with the forcing iteration, then you can deal with a point of cofinality. You can phrase the iteration in such a way that if you deal with cofinality point of conventionality aleph 1, then if you do one thing and something of conventionality aleph 2, then the two things would conflict.
When you discussed Martin's maximum, you said that the stationary preserving forcing is it's a kind of the strongest.
Yeah.
But when we look at the formulation of Martin's maximum, it is that you want to meet aleph 1 dense set. Well, I mean, a beginner might say that, well, you want to meet aleph 1 dense sets. No wonder your continuum is aleph 2 because it's the next one. Why don't you? What if you want to meet aleph 2 dense sets, but then maybe continuum is aleph 3 or something like that?
No, you can't. No.
I know you can't, but
No. The point is that you can't.
you can't. Yes, but maybe it is because of the concept of almost proper that and aleph 1 are somehow tied together.
No, but forget about the fact that it ends up in that under being stationary preserving is the same thing as semi-proper, whatever that means. But nothing to do with it. The fact that if you try, I mean, if you assume that this forcing axiom for large kernel becomes stronger, and simply again you run exactly into the block, the aleph 2 barrier. If you try to have a forcing axiom which deals with meeting more than aleph 1 sets of this kind, you run exactly into the aleph 2 barrier. I mean, you can have some kind of forcing axiom, special cases of forcing axiom that deal with more than aleph 2, but they are so special. I mean, what you do? Let me try and get you the feeling of what's going on. What's going on is as follows. You are trying. I mean, the forcing axiom tells you the following thing: you live in a certain universe of set theory. You say you can imagine a bigger universe in which there exists a set satisfying a certain property. Okay? In the bigger universe, you'll find it. You want to argue the forcing axiom got the intuition that tells you that there exists something that, to a large extent, like this one, which is in the ground. The model is rich enough. You really don't have to go out. It's already there, the thing you assumed. And the point is, what do you mean that it's already there? You don't mean literally the same set. I mean, you mean something that is similar to the set, something that behaves like the set X in V star. You have something that behaves here. And the point is what type of requirements you can put, how similar it could be, what type of requirements you can put on the set X, which in the ground model. It depends how many kind of list of properties that they can make. So if you make a list of aleph 0 many things, then it's trivial. You don't get anything new. Then you can imitate. It's simply the fact, people know forcing, it's simply the fact that if you force over a countable model, then you can always find a generic object over the countable model. So the first thing that is interesting, if you say, okay, then I've got not aleph 0 requirements, I've got aleph 1, list of aleph 1 many requirements to get something meaningful. Okay? Then aleph 1, fine. So now let's try and require more, aleph 2. The point is that if you look at for the class of forcing that you're talking about, the stationary preserving, or even proper, or every relatively small subclass of proper, you can't go past. You can't have it for aleph 2. There is a barrier there that blocks you from passing aleph 2. So the only meaningful, actually in my presentation, the way I phrased it for anything less than the continuum. Suppose you phrase Martin maximum in the sense that you can meet every less than continuum many things. Then this statement implies the continuum is at most aleph 2. The case aleph 0 is trivial, doesn't give you anything meaningful, and so there is something natural about aleph 2 being a natural, seems like a natural barrier. Of course, if for instance, the conjecture about the nice evidence, for the size of the continuum will be true, that will be another evidence for the naturality of of the barrier of Aleph 2. Now again, I'm not saying that this is the only. Again, these are ways in which you can try and pick the more convincing set theory. Again, I'm not saying necessarily this is going to be adapted. Again, this is something that looks appealing, looks promising. Time will tell us what will come up as the natural direction.
We have to have it figured out by the big master workshop involving multiple speakers.
Yeah. Well, there will be fights there, I'm sure, but I want to